Hello everyone, welcome back to the How series. We are beginning the last session of the workshop Programming and Optimization for Intel Architecture. In today's session, we will talk about performance optimization and focus on techniques specific to the access to caches and main memory. You can watch recordings of past presentations, download my slides, code on the course web page. At the bottom of the page is a chat window, and in this chat window, feel free to ask questions as I speak. Myself or my colleagues will address these questions as we go. For more extended questions, feel free to use our forums. And finally, make sure that you take advantage of the remaining few days of access to the Colfax cluster. This is a cluster equipped with multi-core Intel Xeon processors, many core Intel Xeon Phi co-processors and processors, and you can use it to run your code or our exercises for the entire 2 weeks of the workshop. This is the final session of the performance optimization module, and hopefully I've convinced you that it is possible to design optimized applications in such a way that a single code can work on multi-core processors and many core coprocessors. The same techniques will also make it ready for the upcoming generations of Intel architecture. To make this happen, we structure performance optimization techniques into 5 areas which really address the fundamental building blocks of modern processors. Today, we are going to focus on performance optimization techniques useful for memory access tuning. When you talk about tuning the memory traffic, there are 2 aspects to it. Data locality in space and locality in time. We already covered data locality in space. Techniques related to this topic really overlap with the optimization of vectorization and multi-threading. Specifically, when we talked about vectorization, we talked about unit stride access, when we talked about multi-threading, we mentioned affinity, which makes the threads stay local to the cached data, and we talked about NUMA-friendly practices, particularly parallel first touch. Most of what we will do today has to do with data access locality in time, which is a prerequisite for efficient cache utilization. To remind you what caches are and how they're organized, I'm showing this diagram of memory organization of a Xeon processor. This is a traditional 2-way multi-core CPU. You have cores operating on data in registers. Behind the registers is a tiny level 1 cache. It is very fast and it is local per core. As long as your data is in the level 1 cache, you can efficiently grab it. But if you have to evict some of the data, it may stick in the larger but slower level 2 cache, which is also per core. Behind the level 2 cache is the last level cache, which is shared across all of the cores in the chip. Some modern processors will have 2 slices of the last level cache because cores are organized into 2 rings. And behind the level 2 cache, behind the last level cache, is the on-platform memory. In the case of a 2-way processor, this is just the organization of one package. There is a quick path interconnect connecting this package to the other package with its own memory and cores. And every core can transparently fetch data from remote memory or from local memory, but remote memory access is more costly. In Xeon Phi, the situation is similar. We saw this in session 1, but there is no last level cache. Instead of the last level cache, Xeon Phi cores can access the memory, the onboard memory that lives on the PCI Express add-in card. To access the memory of the host, you have to go across the PCI Express bus, and for that you will have to use an offload framework. If your Xeon Phi is a second generation bootable processor, then again you have cores level 1 cache, level 2 cache, and on-package high bandwidth memory. But in contrast with the coprocessor, you can transparently talk to the on-platform memory. The high bandwidth memory may be used as a flat memory region or as a cache. We will talk about this today. Whichever level of memory hierarchy you're communicating with, data is transferred in increments of cache lines. A cache line is the minimal block of data that can be transferred between different levels in the memory hierarchy. They are 64 bytes long in all Intel architecture processors and aligned on 64-byte boundaries. Cache lines give parallelism to memory traffic, because whenever a core requests a single double precision number, it gets that number and also 7 of its neighbors in parallel. Single precision, you get one number and 15 of its neighbors for free. You have to exploit that parallelism in memory by keeping data access local. Particularly, you have to use unistride so that when you get this number and get all the free numbers, you take advantage of them. And also, so that if you have to visit many cache lines, and some of them get evicted from the registers, if you have to visit many cache lines, you have to revisit the ones that you've already visited soon enough while they're still in registers or in a high-level cache. This is what memory reuse techniques. This is what techniques centered around memory reuse rely on. To motivate what we're going to do today, I want to remind you a couple of slides that we've already seen. I mentioned that loop vectorization is great, but vector mathematics is so cheap that when you have success with vectorization, you need to focus on memory access. Because if you don't optimize cache usage, vectorization will not matter. You will be bottlenecked by memory access. I've made the statement that vector arithmetic is cheap. Now let me put some numbers to that statement, to that claim. Take an Intel Xeon Phi processor 7250. This is the nice landing architecture. It has 68 cores. They're clocked at 1.2 gigahertz when they work on vector math. In double precision, each cycle processes a vector with 8 vector lanes. And if you're doing fuse, multiply, add, then the throughput is 2 instructions per cycle. I'm sorry, then you're doing 2 instructions per operation, and the throughput is 2 instructions per cycle. The product of all these numbers is the theoretical peak performance of the processor. It is 2.6 teraflops per second, 2.6 trillion floating point operations per second in double precision. Now ask yourself the question. Well, you want to perform 2.6 trillion floating point operations. How much data is there in 2.6 trillion floating point numbers? Well, multiplied by 8 bytes, you get 21 terabytes. So your cores want to consume 21 terabytes of data per second, but if you get this data from memory, then even the high bandwidth memory can deliver only half a terabyte per second. So there is a disconnect by a factor of 40 between the performance of math and the performance of memory. The only way you can keep your cores saturated, meaning the only way you can achieve the theoretical peak performance, is when you do reuse data. Because if this data is not coming from memory, but rather it's coming from caches or registers, well, you will get greater bandwidth. So before your data leaves registers on Xeon Phi, you have to reuse every floating point number 50 times. If you have 50 floating point operations for every true memory access, then your application has a chance of being compute bound. If you do fewer than floating point operations per memory access before your data leaves memory, then if your memory traffic is sequential, you're bandwidth bound, or worst case, if your memory traffic is very scattered, you're latency bound. There is a way to estimate, that number 43 that I estimated in the previous slide is based on the performance of the fused multiply add operation. The amount of reuse that you have to have is not as high if you're doing different kind of math. Well, if instead of fuse multiply add you're doing exponentials and reciprocals, the throughput is a factor of 4 to 6 lower. And if you do really heavyweight operations, then the throughput is 20 times lower, so you barely need any data reuse. Compare it to the latency and throughput of memory accesses. Contiguous load from the level 1 cache gives you a throughput of the receivable throughput of half a cycle. So you load 2 cache lines per cycle, and you can consume 2 cache lines per cycle. So if your data is coming from the level 1 cache, you're fine. But if your data is not accessed contiguously, rather you're gathering or scattering, then your memory access is at best an order of magnitude lower. If you're going to a lower level cache like level 2 or high bandwidth or MCDRAM as cache, then it's even lower. These are the numbers that you have to keep in mind, and there is a way to visualize what you're going to get with it with a roofline diagram. I will explain the roofline diagram in a minute. The only reason why you would use the same number multiple times in memory is if your algorithm has data reuse. Some algorithms don't have data reuse, and their complexity is O of n, where n is the data size. For example, if you have an array and you want to scale this array, you probably don't have any data reuse. A similar operation, taking an image and adjusting its brightness, also has no data reuse, or vector dot product, no data reuse. Unless, of course, the higher level algorithm reuses these images that you're scaling, or vectors that you're computing the dot product of. These algorithms are typically memory bound, unless the number of times that you use each data element is large. Other algorithms that have stronger arithmetic complexity naturally have data reuse. For example, matrix multiplication has a complexity of n to power 3/2. Here n is actually the number of elements in the matrix, not the number of rows, but the number of elements. The n-body calculation that we optimized in session 6 also scales non-linearly as n squared. So naturally, each element is used n to power alpha minus 1 times, when your complexity is n to power alpha. So the greater the value of n, the more reuse you can have. And here, it is particularly important to have a good implementation that actually does reuse data when it's needed. A good implementation can be compute bound for such algorithms, but a poor implementation will be memory bound, like we saw for the n-body calculation. Some algorithms can never be compute bound. Sorry. There is a convenient tool to visualize the relationship between how much data cores want and how much data memory can deliver. I'm talking about the roofline model. The roofline model is an analytical tool for predicting what you can do to optimize your performance from the memory access point of view. The roofline model is a function on the space where the x-axis is arithmetic intensity, the y-axis is performance. Arithmetic intensity is just how many times you reuse every element fetched from memory while it is still in registers or in caches. For infinite arithmetic intensity, you can draw a flat line, meaning that however many times you reuse your data, you can not get better performance than the theoretical peak performance of your chip. For arithmetic intensity of 1, well, you can divide the bandwidth by the size of the data type, and it will give you how many floating point operations you can perform. Then you connect this dot to that asymptote with a unit slope line, and you get your roofline model. This break will occur at exactly that point, that 43 that we estimated a few slides ago. So this is when you break even between memory access and communication. Why is it useful? It is useful because if you can actually compute the arithmetic intensity for your algorithm, the way it's written on paper, and this arithmetic intensity hits the sloping part of the roof, then you can improve your performance by increasing the arithmetic intensity, by increasing data reuse. I will talk about the specific techniques for doing that today. The roofline model that I've shown is for MCDRAM bandwidth and for the fuse multiply add operation. If you have a different kind of operation for which you want to draw the roofline model, you need to draw a different ceiling. For example, this is for the exponential and reciprocal functions. If you're dealing with caches, then draw a higher bandwidth. If you're dealing with DDR4, draw a lower bandwidth. So your roofline model may depend on the data size and on the type of operations. You can read more about it in this paper. This link is clickable. So how do you increase arithmetic intensity? I will discuss several techniques, all of them centered around loop transformations. The first one is loop permutation. The idea with loop permutation is if you have an algorithm that has nested loops, sometimes you can permute or swap the loops to maintain unistride memory access. Here I'm illustrating access pattern to a matrix, where the matrix is stored in the row major format. So this row is stored here. This row is stored there, and so on. Suppose I'm doing something like matrix vector multiplication, and I need to visit each element once. If I go column first, row next, then I get unistride access. And I'm taking advantage of cache lines. I'm reading this number, I get 7 neighbors for free. So these are free accesses. Then I'm reading the next number, and I get 7 neighbors for free. If I do matrix vector multiplication, then the arithmetic intensity is 1 in this code. and 1 is not 40. But it could be worse. It would be worse if we change the order in which we visit elements to that order by just permuting loops. Then, in memory, I read this element, and then I jump to another element. And then I jump to the next element. Because of these jumps, I don't use cached lines efficiently. Well, for this particular example, I have this is the width of the cached line, so I'm using 2 elements out of 8. So yeah, and if my matrix is very tall, then by the time I finish with the matrix, I may lose these cached lines from registers. So at worst, my arithmetic intensity is 2 out of 8. So this has arithmetic intensity. For this one, the arithmetic intensity is 1. For that one, it's 1/4. 1/4. The compiler is actually trained to recognize opportunities for loop permutation, and it is trained to look for unistride access. But sometimes the compiler may not be able to permute loops for you. This might happen if loops are not perfectly nested, or if you're using OpenMP. I'm showing you an example of 2 codes in which loop permutation could help. A full disclaimer, this is the code of matrix vector multiplication. And the 2 versions that I'm showing you here are bad code and an even worse code. Even worse. Good code for matrix multiplication is not trivial, and really, instead of writing loops, you should go for a BLAS library, basic linear algebra subroutines. For Intel architecture, the math kernel library that comes with the compiler, or you can download it for free, this library has a good implementation of matrix multiplication. I'm showing you a bad code and an even worse code just to give you a hint on how to spot bad memory access pattern. The definition of this operation is Cij equals to the sum with respect to k of aik bkj. And if I naively write down this expression as 3 loops, I will have ijk. If I permute these loops, I will have order ikj. My claim is that ikj is better than ijk. And that's why. If your inner loop is in k, then this is a constant, so you don't move in memory with respect to k. This gives you unit stride, which is good. But here, k is multiplied by n. So when I increment k by 1, I jump in memory by many locations, and I have poor data reuse inside the cache line. So this is strided. In contrast, the ikj order gives you unit stride. This gives you a constant, and this is unit stride. So this is how you can spot by eye opportunities for loop permutation. If you can permute loops, or sometimes if you can transpose data structures, you could get better performance. The compiler might interchange loops for you, but not in complex cases. In complex cases, you need to investigate it manually, and sometimes it makes sense to look at not just loop permutation, but also data transposition. So there you go. Loop permutation is one of the techniques that you can use to increase your arithmetic intensity. Another technique to increase the arithmetic intensity is loop fusion. Well, loop fusion is the opposite of loop splitting. If the nature of your application is such that you have a series of loops, and if the logic of the application allows you to rewrite this series of loops as one loop with the series of operations from the original loops, then this is Loop Fusion. And Loop Fusion can be good for your memory access. In this example, I have some array called data. And I'm putting this array through multiple stages of processing. Data is not necessarily comprised of, doesn't necessarily comprise floating point numbers, just some abstract data set. I initialize it, stage 1, stage 2. In the first version, I have to read the entire array data. If it fits in caches, no problem. But if it doesn't fit in caches, then I will not be able to store the entire array in a cache. And when I revisit all these elements, I will have to go to memory to get them. That's not good, and it can be easily avoided by Loop Fusion. With Loop Fusion, I do the same operations, but in a different order. First, I apply all data processing stages to one data element, and then I move on to the next and the next data element in the loop. Loop Fusion automatically improves data reuse and reduces the pressure on the memory subsystem. There is also a potential positive side effect, or a cherry on top, if you like. Sometimes you may be able to reduce the amount of data that you carry between different stages. For example, if the initialization should spit out some intermediate values, in this case, you will have to store n of those intermediate values and feed them into the second loop. But in the fused loop implementation, you only have to store one intermediate data and pass it to the next function. So this may further reduce the memory footprint and the pressure on the memory subsystem. I will not be able to demonstrate Loop Fusion live due to time limitation, but you can use one of our labs. Lab 409 allows you to experiment with a statistical calculation where we generate random numbers and then compute their statistical properties. Loop Fusion, in that case, improves performance, and you can see how it works. And now I'm moving on to the third technique for arithmetic intensity increase, and that is loop tiling. You need to think about loop tiling when you have data reuse in your algorithm. For example, in this algorithm, some abstract array bj is reused m times. Well, you can see that I sweep through all elements of b in the j loop, but then I sweep through all the same elements when I iterate in the I loop. So each element of b will be reused m times. Suppose that array b is too large to fit in caches. If I write my loops just like this, I from 0 to m, j from 0 to n, what will happen is I will read bj. So I'm sorry, this is my array b. This is b0, b1, b2, b3, and so on. Colors indicate what's happening. So I'm accessing this element in b, and this is time. Accessing this element in b, I've never seen it, so I have to go to memory. This is a cache miss, and I have to endure the latency of the memory access. Then I will read the next element, j equals 1, but the previous element is now cached. Blue means it's sitting in the cache waiting to be reused. In this way, I will keep reading more and more elements until I fill up the cache. And when I have to read the next element, I will have to kick somebody out. In Intel architectures, caches use the least recently used eviction policy, LRU. It means that the element that was least recently used or least recently fetched will be the first to leave the cache when you run out of space. So this goes first. And this way you will keep missing caches, keep going to memory more and more until you reach the end of the J loop, and only the tail of vector B is now cached. When you increment I and start reusing your data, B0, you're ready to reuse it, it's gone from the cache, so sorry, you'll have to go to memory again. Loop tiling is a transformation where I strip mine one of the loops and then do loop permutation. In this case, I strip mined the loop in J, and then I permuted the middle two loops. What it does is it allows me to read just a section of B, and then revisit B0, B1, B2, B3 while they are still in caches, because I didn't read too much data. Eventually, I will process all the elements the required number of times, but for this particular case where m equals 2, I have a 50% cache hit rate. If m was greater, if it was much greater than 1, I would have a cache hit rate close to 100. This flavor of loop tiling when you strip mine the inner loop is called cache blocking. There is a different flavor of loop tiling, which is register blocking. I'm sorry, let me defer that for another minute. I've shown you cache blocking in the diagram. I wanted to show you the same in code. This is the original code. Then I strip mine the loop in J. Nothing changed in terms of memory access yet. And then I take and permute the outer two loops. So now JJ is outside, I is in the middle, J is inside. So you can see, if you isolate yourself from this, you can see that I have a short inner loop. It should be short enough to fit into a cache, and I'm reusing the data accessed by this loop m times. So this is cache blocking. Typically, when you do this permutation, strip mine the inner loop and permute the outer loops, you will want tile to be of order hundreds or thousands if you're dealing with single precision or double precision numbers. These numbers are simply comparable to the size of the level 1 cache, sometimes level 2 cache. If I approach this problem slightly differently, I can derive another flavor of loop tiling, which is register blocking. Same problem, solved differently. I permute the outer loop, and then I strip mine the outer loop, and then I permute the inner loops. What happens now is I read one element in B, and I reuse it many times. Read one element in B, reuse it many times, while it's still in registers. In this case, the cache hit rate, I'm sorry, this is incorrect. It should be 75%. You can see the ratio of yellow to red is 3. In code, it looks like this. Strip mine the outer loop in I, and then permute the inner two loops. So now it's I, J, and then I. If you wanted to retain vectorization in J, you put pragma simd here. Because now a new loop is inside, so if you wanted to retain vectorization in J, if J is what gives you unit stride, then you have to direct the compiler's attention to that. It's a little difficult to understand what's happening there, so it's the same code, only rewritten as double loop tiling, where I have I, JJ, IJ. They have two different tile sizes. These are tuning parameters. This tile will typically be of order between 1 and 10. And this will typically be the vector length or twice the vector length, so something like 16 or 32, and so on. In this implementation, it is just plain to see that J is the loop that's going to get vectorized. We will experiment with loop tiling in the practical part of today's presentation. But To be honest, this is the only technique where I cannot guarantee good code portability. The reason for that is that the tile size is a tuning parameter. It has to be small enough to allow data reuse and large enough to take advantage of the entire cache size. So when you port across different architectures, you have to change the value of the tuning parameters. Because this is not ideal, and because you don't always want to calibrate the code, there are techniques that are more resilient to changes in the platform or to imprecise estimation of the tuning parameters. These techniques are generally called cache oblivious methods, and they are built on recursive divide and conquer. Qualitatively, I can illustrate cache oblivious algorithms in this plot. What I'm showing here is some sort of a matrix, and I have small elements indicating maybe floating point numbers, small squares, and large squares indicate tiles. So if I have to process each element in this matrix many times, I can tile the matrix, and then I take one tile and I do data reuse while I can. Then I move on to the next tile, and then I do data reuse. Move on to the next tile and data reuse. Typically, I will have more than one container. For example, with matrix-matrix multiplication, I will have another container. And it may happen that one container likes you to traverse tiles left to right, then down, and another container might like the opposite order. Also, the tile size is very sensitive to the cache size, so moving the code from one architecture to the other, you may have to change the tile size. To work around these limitations, you can change the order in which you traverse tiles. This is what cache oblivious divide and conquer will do. Instead of traversing tiles like this, or traversing the tiles like this, you are going to traverse tiles like that. And that is your cache oblivious algorithm. Why is it called cache oblivious? Well, the order in which you traverse tiles is self-similar. So, if your optimal tile size for this architecture is actually this much, but your code uses a smaller tile size, it is still okay, because as you recurse out, you will stay within that tile. Well, this is qualitatively correct, I believe. How do you derive this pattern? You derive this pattern by recursive divide and conquer. Take a look at the matrix. Is it too wide or too tall? If too wide, split it like this, and then recurse into the left-hand side. Now it's too tall. I split like this, recurse in the top part. Too wide, too tall, too wide, too tall. Oops, reached a threshold. You have to set a threshold on this recursion, and when you reach the threshold, you do a linear algorithm. After that, you start recursing out. This is the next tile to visit, the next tile, and so on. This is how you achieve this pattern. There are applications out there using cache oblivious algorithms. One of the most well-known ones is the FFTW, the FFTW library. FFTW stands for fastest Fourier transform in the West, and the people who wrote the FFTW library are also the people who are behind the invention of cache oblivious algorithms. FFTW uses cache oblivious recursion to optimize cache utilization. So we are going to work on an example to illustrate loop tiling. And I will demonstrate one example just on paper, and one example I will demonstrate live. For the first example, consider matrix transposition. Matrix transposition looks easy on paper. Bij equals to Aj. It has no math, so the arithmetic intensity is formally 0, or you can say 1, because you copy. The difficulty in computer architecture is that, well, the assumption is that A and B have the same type of layout, row major for both, or column major for both, because if they have different layout, then you don't need to transpose, you just copy. In transposition, you will have to go in I from 0 to n, in j from 0 to n, and depending on which order you choose, you will either have unistride in A and strided axis in B, or vice versa, strided axis in B, unistride in A. Unistride axis is good, but strided axis is bad because when you stride in memory, you touch only one element in every cache line that you get. It is okay if you touch just a few cache lines, enough, not too many cache lines so that they're still in registers, and then you return to that cache line and start revisiting data. So as long as the matrix is small, the plain algorithm will work very well. But what if the matrix is large? If the matrix is large, you can actually split it up into smaller matrices and transpose them tile by tile. This will give you data reuse in registers. And instead of arithmetic intensity of 1/8 or 1/16, you will have arithmetic intensity of 1. This is the plain algorithm for matrix transposition, and this is the tiled algorithm. It only works when n is a multiple of tile, but with that limitation, it's easy to understand. So I'm splitting my code, my big matrix, into many small matrices, 200 by 200. This is just the tuning parameter. And inside this small submatrix, I just do matrix transposition. And then I iterate over the tiles in my matrix until I'm done with all the work. This is out-of-place transposition of square matrices. On the previous page, there was a link. If you click it, you will be taken to the paper where I demonstrate loop tiling, measure performance for matrix transposition. Also, it demonstrates cache-oblivious algorithm in this code. The second example that I wanted to demonstrate is matrix vector multiplication with tiling. And this is what I will do live. Matrix vector multiplication is AB equals C, where C is computed like this, Aij, Bj, sum over J. It seems like a great fit for Intel architecture. Parallelize the outer loop, the loop over I. Vectorize the inner loop, the loop over J. Sounds like a good idea. The loop in J gives you unistride access to A and unistride access to B. The loop over I is also good to parallelize because you are going to distribute different values of I to different threads, and when you write to memory, each thread writes to its own location. If vector C is, well, if you use default static scheduling, false sharing will be minimal. But I think that in this code, if B is large, you will end up getting only half the performance that you are entitled to. How is that? Well, what are you doing in this algorithm? You have matrix A, and let's assume that it is in the tens of megabytes, so larger than any cache. You have B. Let's assume that it is in the kilobytes, so small enough to fit in a cache. Definitely A has many more elements than B. For every element that you read from A, you do two operations: multiply, add. So your arithmetic intensity is equal to 2 operations per memory access. If that's the case, you can estimate the maximum performance. If you have a bandwidth of 100 gigabytes per second, no, let's do it differently. You can estimate the maximum performance. Just compute how long it takes to read matrix A, and compute the number of floating point operations, divide operations by time, you will get performance in gigaflops per second. The problem is with vector B. If B doesn't fit in, say, the level 1 cache, but only fits in level 2, or even spills out of level 2, then you might end up rereading vector B from memory m times. So you will have the time to read A plus the time to read B as the total time of your calculation. And if B is read from memory every time, then the time to read B is actually equal to the time to read A, because A has m times n elements, and B has n elements reused m times. So if you're not careful about loop tiling, you may get performance twice lower than it could be. We will apply loop tiling to this algorithm, and we will see what comes out of it on the cluster. For this exercise, go to How Serious Labs, session chapter 4, and then lab 408. Main CC is what you want. And this is my matrix. So n is 2 to the power 19. This is 500,000. M is 2 to the power 10, which is 1024. And I will start with the plain algorithm for matrix vector multiplication without any optimization. Well, I shouldn't say without any optimization. After all, it's parallelized and vectorized, but I don't already consider it optimization because, well, no memory access optimization. Compiling as usual for the CPU, for Knight's Corner and for Knight Plenty. Submitting for all of them. And creating a log. So Xeon has the Ivy Bridge architecture. We have a Xeon Phi coprocessor with Knight's Corner architecture, and we have a Xeon Phi processor with a Knight's Landing architecture. The values of performance that I'm going to record are measured in gigaflops per second. These are the values. CPU gives us 15.9. Xeon Phi gives us 31.9, and Knights Landing 75.6 gigaflops per second. So what would we expect? So let's do it like this. So if we have m times n elements times 4 bytes, this is the amount of data in the matrix. Actually, the amount 8 bytes. We're doing double precision, right? 8 bytes. This is amount of data. Floating point operations are m times n times 2. For every element, we do 2 operations, 1 addition, 1 multiplication. So if we are limited by memory bandwidth, then the amount of time for memory access is the amount of data divided by bandwidth. And so performance in gigaflops per second is flops divided by delta t, which is m times n times 2 divided by m times n times 8 bytes, and this whole thing multiplied by bandwidth. So this cancels out, and I end up with bandwidth divided by 4. So bandwidth in gigabytes per second divided by 4 is performance in gigaflops per second. Dirty calculation, but correct. So the expectation that I have for the Xeon is of order 20 gigaflops per second. For Xeon Phi, it is of order of 180, I think 45 gigaflops per second. And for Xeon Phi, the expectation is, I think, 90 gigaflops per second. Why these numbers? That's because the bandwidth of the stream benchmark for Xeon Phi is 80 gigabytes per second. For the Xeon, something like 100, I don't remember the exact number, 180 gigabytes per second for Xeon Phi, and something like 360 gigabytes per second for reading from the high bandwidth memory. This number divided by 4 is the expectation in gigaflops per second. Sorry for a lot of boring math, but what we see is that we actually start not so bad. We are close to the peak performance. Before I even go and try to optimize data reuse, I want to take advantage of the knowledge that we gained yesterday. This is a bandwidth-bound application, so we are better off tuning affinity. Particularly for bandwidth bound, this seems to work well. KMP hardware subset equals 1 thread per core, and KMP affinity scatter. So this will use 1 thread per core, which is good for bandwidth bound applications, and it will spread the cores across the platform to even out the load on memory controllers. I will do it for KNC, and I will do it for KNL. So submitting to the queue, and let's record updated baseline. Almost done. So the last three numbers are the updated values, 18.1, KNC is not feeling so well. KNL neither. So I guess because they're trying to reuse data, maybe we should give them a few more threads per core. So how about a few threads per core? How about we go and so for KNC, let's use 2 threads per core. KNL, 2 threads per core. Will that make it better? Sorry. This is the command. Not good either. Well, let's restore 4 threads per core, and I think we will get back to the original baseline. So when we tuned Affinity, we set Affinity, we actually only did it on Xeon Phi. So we should get the same results for Xeon Phi, KNC, and KNL. So I can never remember a good way to show what's happening. Okay, 31.5, 77. We are starting pretty close to the target. Only 10% to go on the Xeon. Well, up to 50% to go on Knight's Corner, and something like 15% to go on Knight's Landing. So I don't expect anything dramatic, but at least we will see that it works. And when we see that it works, we will actually make use of all of the techniques that we studied earlier. Usually loop tiling gives huge performance benefits. Often loop tiling gives huge performance benefits. For example, in session 6 in the n-body simulation, the effect of loop tiling was 5x on KNC and 3x on the on Knight's Landing. This time we expect more moderate speedups, but that's due to the nature of the problem. We already start with a well-optimized calculation. So the problem with this code is that n is too long. Remember, n is 500,000. So the amount of data in vector B is 4 megabytes. 4 megabytes is too big for the level 2 cache. So on the CPU, it may still fit into the last level cache. That's why it's doing well. But on Xeon Phis, it will spill and you will have to go to memory to fetch it. The solution is clearly to make this loop shorter. I will strip mine this loop to make the innermost loop shorter. This is going to be step 1. When I strip mine the loop, the outer loop now has a stride. The inner loop now goes from the outer loop index to the next one. But this is not going to improve memory usage because we do the same operations in the same order. Memory access is going to be improved when we do step 2, loop permutation. So once again, step 1, strip mine. Step 2, permute. Well, we did both of these steps, and I can definitely try to run the code, but I think we're looking for a disappointment. JTile, I have to define JTile. Usually, when you strip mine the inner loop and you're working with floating point numbers, good values of JTile are in the hundreds or thousands, so that you fill up the level 1 cache. Our level 1 cache is 32 kilobytes, so how about this 32 kilobytes divided by 8? 8 bytes per number, something like this. Only I have to make it long. Okay, I define JTile, submitting to the queue. It's called JTile. The performance is slightly better, 19.5, but I have a complaint from the correctness checker. So we did loop tiling, and we got incorrect results. So no wonder the compiler wasn't able to do this automatically. You can definitely see what the problem is. The problem is that after loop tiling, we are parallelizing the loop in JJ. So different values of JJ go to different threads. But within a thread, it is likely that different threads will have the same value of I. So this is a data race. Well, we know what to do with this kind of data races. We've done it several times in this course, and we will do that. But I think it's a good time for coffee before we move on to this step. So after the break, after the 5-minute break, we're going to resume, resolve the data race, and move on with optimization. Okay, enjoy your coffee if you're drinking coffee, and I will talk to you in 5 minutes. Okay, with more energy, I think I can handle this code. So the problem was that we have a data race on vector C, but the only thing we're doing with vector C is incrementing it. So we will waste no time trying to insert mutexes. Instead, we will go right for the reduction clause. So we're going to do reduction for the addition operator on vector C. If we leave it like this, we know that OpenMP will complain. The C is formally a pointer, and for reduction on arrays, you need to specify a slice. So the entire C has to be reduced. Seems to work. I should have probably executed on all of them. So loop tiling. Almost done. The last three values are our updated performance results. The CPU gives us 19.6 gigaflops per second. Knight's Corner 32.1 gigaflops per second, and Knight's Landing 81.7 gigaflops per second. So we achieved a small speed up. That's not bad, but when I look back at my code, I find that I'm not happy. Well, this is a tuning parameter, and you can experiment with different values of it. Well, so what if it was 2048, right? I don't know ahead of time, so I need to experiment. Okay, let's try. So now CPU is 20.6, Knight's Corner 32.7, Knight's Landing 7.6. So it looks like we are going in the right direction for the CPU, but in the wrong direction for Knight's Landing. What about the opposite direction? So make it 8,000. I'm not going to waste your time trying too many values. I've tried them before, and I know that we're in the right ballpark. But I want to show you what you would do if tuning parameters are different for different platforms. Okay, that doesn't seem to work for any of them. Okay, 18. $29 and 62. So looks like the optimal value for the CPU is this for the Knight's Corner, this for Knight's Landing, that, which is 4,000. So commonly you will see statements like that. If defined KNL tile, which is a user-defined preprocessor macro, then set JTile to 4,000. Otherwise, do that. The reason I'm doing preprocessor macros as opposed to an if statement is that sometimes compilers are able to better optimize when the values of loop tiling constants are known at compilation time. So KNL tile is actually a preprocessor macro that I specify when I compile for Knight's Landing. By doing that, I will use this value for Knight's Corner and this value for Knight's Landing. Well, it's predictable what we're going to get, so I'm not going to wait for results. Another aspect that I want to point your attention n is 2 to power 19. JTile for Knight's Landing is 2 to power 12. So how many iterations do we have in this loop? Only 2 to power 7, which is 128. This is a fortunate number for Knight's Landing because we have 64 cores. But you can see that if we had 68 cores or 72, that would be an inconvenient number. Or if this was just slightly higher, we would not have enough iterations for the Knight's Landing processor. It illustrates what I promised I would show you when we dealt with insufficient parallelism in session 8. Remember, we had a matrix that was very short but very wide. And I said, well, this is a dramatic shape, but you can get from more regular shapes towards these dramatic shapes when you apply a different optimization, which is loop tiling. And this is exactly what happened. We thinned out the outer loop so much that we have too few iterations. So maybe we could do slightly better if we also did what we did in that problem with the short and wide matrix, which is loop collapse. We can collapse 2 levels of loop nesting. This is probably safe because vectorization is applied to the 3rd level. And I can run. Now with loop collapse, we have plenty of iterations to parallelize across, and it should work out better. So now we get 20.7. $31.6 and 64.9. In fact, you can see that for Knight's Landing it didn't work out well. And this is where the pain of tiled algorithms starts. Because maybe this is the good loop order, maybe you can permute the loops. Maybe you have to strip mine also this loop and introduce another tiling constant. And in fact, this is the case. if you do a lot of experiments, you can find the solution that we present in instruction 2. Look what I'm doing here. I'm declaring JTile and iTile separately. Well, this is not a very elegant way to do reduction. Actually, this is an old code that was developed before OpenMP had the opportunity to do reduction. Reduction plus on C from 0 to M. And then we don't need any of this. It will be just easier to see what we're doing. So now with OpenMP 4.5, we don't need all that. This is what we need, but you can see that I have double tiling. I've played with the order of loop nesting, I've played with the tile sizes, and hopefully it works better. The make file, let's get it here. This is of course not satisfactory. It looks like I'm an acrobat trying to keep balance on a tightrope. But this is the nature of tiled algorithms. Thankfully, as I mentioned, there are also cache oblivious algorithms that are a little bit less sensitive to these kind of subtleties. Well, seems good enough to record. So now 21.8, 37.7, and 74.9. I guess this is not the optimal tile size for Knight's Landing. For Knight's Landing, we might use a bigger tile. But yeah, hopefully you get the point. It's very finicky. Unfortunately, I don't have enough time to walk you through the cache oblivious recursion solution. I'm sorry, I don't have the time to do it live, but I have the time to walk you. So the cache oblivious recursion will look like this. In the main program, I will still call the multiply function, but my multiply function will have a twist. It starts threads, restricts execution to one thread, and then calls a different function which is actually recursive. So the multiply function is just a wrapper for the recursive function. What happens in this recursive function is I check if I've reached the threshold, and if I've reached the threshold, I process the smallest tile like this. Then I check, is my matrix too tall? If it's too tall, I split it vertically, and I recursively process the top and the bottom part of the matrix. I use a functionality that we did not discuss, I only briefly mentioned, OpenMP tasks. The OpenMP task functionality puts this function call in a queue for execution sometime in the future. It may execute it immediately, and most of the time it will, but control will return immediately to the original function, and I will proceed with the second recursive call. So these recursive calls are going to be executed at the same time. You can think of it like this. Then I wait for the tasks to finish and do reduction. And then I do the same kind of approach, but this is the branch that's taken if the matrix is too wide. I still have to define some tuning parameters, like this threshold. But I have more room for error in the values of these parameters. And the result, I think, is also better. Submitting to the queue, and let's see how it works. Not an easy code, but conceptually straightforward. Split the matrix until it's small enough, and then recurse out. So I get 21.2, close to the optimum. This is a record, 42.0. And this is good, 77.5. So this is the game that you can play with loop tiling. The effect of this optimization was not dramatic in this example because we already started with a well-performing code. In other cases, like what you saw in the n-body simulation, loop tiling can make your performance jump by a huge factor. And you can see it from the roofline diagram. What loop tiling does is it moves your code to the right on the roofline diagram. Earlier in this presentation, we talked about data locality and about making better reuse of data in caches. Caches are definitely a very important level of memory hierarchy, and caches are important when you have data reuse because they allow you to revisit data sooner, faster than you originally fetched it. In the rest of this presentation, I will talk about a different case where you have no data reuse. And I will talk about bandwidth tuning. So if you have data reuse, you need to use caches, and you need to do all these loop transformations, loop permutation, fusion, and tiling, and optionally cache oblivious recursion. All to improve data reuse in caches. If you have no data reuse, then to optimize memory traffic, you need to look into the techniques for memory bandwidth tuning. There is a convenient benchmark that you can use as an example of how well your code can perform. It is called Stream, and you can download it from its developer's website. We will actually do it live. It performs 4 tests: copy, add, scale, and triad on large arrays, exercising all threads. It uses OpenMP. And we will see how to optimize this benchmark to run well on an Intel Xeon 5 processor with high bandwidth memory, and also how to take advantage of the high bandwidth memory. I will demonstrate the importance of compiling with the right argument, using the right data size, using the correct affinity and core count, and possibly tuning prefetching, although I think I don't have to do this anymore because I think the compiler does a good job. The idea here is that by seeing how to optimize the environment of the Stream benchmark, you will be able to better see what you have to do for your application if it is bandwidth bound. I will also mention streaming stores, and before I jump into code, I want to explain what this is. Streaming stores are instructions to store data from registers into memory, bypassing caches. Normally, when you tell the core to store data in memory, it will say, memory subsystem, here's a piece of data, store it. It will likely stick in the level 1 cache until it gets evicted and needs to be propagated down, which is good if you are going to reuse this piece of data. But we are talking about codes that do not have data reuse. For these codes, it makes sense to do streaming stores when you bypass caches and write data directly into memory. This leaves more of the cache available for variables that you do reuse. To request streaming stores, you can use the directive pragma vector non-temporal before you loop, or on the level of a single file, you can use the argument qopt streaming stores always. I will also talk about high bandwidth memory in the hands-on exercise, and I want to remind you what that is. High bandwidth memory is available in Knights Landing processors. It is based on the MCDRAM technology, and it is 16 gigabytes in size. The high bandwidth memory can be used in one of the two modes, cache mode or flat mode. Cache mode means that the operating system doesn't see MCDRAM. MCDRAM sits between the CPU and DDR4. If you fetch some data from DDR4, it sticks in MCDRAM. So if you revisit it, you get faster bandwidth. Not latency, just faster bandwidth. Flat mode means that the operating system sees MCDRAM, and you have a special allocator to put your data there. I mentioned NUMA-CTL yesterday. It is a tool to identify the NUMA architecture and control NUMA policies. It is actually useful for Knights Landing in flat mode because MCDRAM will be identified as one of the NUMA nodes, which is good news. The tool that you already know how to use, you can apply to run the application in high bandwidth memory. That said, let's jump into the code. I promised that we will download that benchmark, and we will. To download the stream benchmark, go to source code directory, find the stream benchmark. It's available in C and in Fortran. I'll just copy the link, and I will go here. Let's create stream and new directory, and I will use wget to download the code of the stream benchmark. That's all I need. The benchmark is not very long, half a thousand lines, and it's easy to find what's happening. It allocates 3 arrays, A, B, and C. They are all large arrays. And then it performs 4 tests with them: copy, scale, add, and triad. The tests themselves look very clear. The copy test is this. Copy array A into array C. The scale test is this. Read array C, multiply by a number, and write into array B. And there's also add, read 2 arrays, write 1 array. And there's triad. Read 2 arrays, scale 1 by a number, and write back into memory. So let's compile and run this benchmark. There's no makefile, so I'll have to make do. We will just do the test on a Knights Landing processor. This returns a bunch of warnings: unrecognized OpenMP pragma. That is because stream uses OpenMP for threading, and I did not include the argument qopenmp that tells the compiler to recognize OpenMP directives. And another mistake that I made by habit, out of habit, I am using the Intel C++ compiler, where this is actually a C file. So I need to use the Intel C compiler. Okay, now it's compiled. I can run it on the login node, no harm in that. And you can see that on the login node, I get something like 40 gigabytes per second. Okay, now let's submit it for execution on one of the compute nodes. But make sure that we request one of the nice landing nodes in the flat memory mode. I will call it, yeah, just that. Oh, I'm sorry, it's not qstat. I should have typed qsub. So here it is running. And you can see that, well, the results are mixed. The add test is doing slightly faster than on the login node. Triad is about the same as on the login node. The coincidence is probably not completely random. Both nodes use DDR4 memory. If I wanted to automatically take advantage of the high bandwidth memory, I could just request one of the nodes with the cache topology. And because the stream benchmark runs tests many times, I should naturally take advantage of this high bandwidth memory. Let's see what we get. Yeah, so out of box, I get of order 200 gigabytes per second. So if you run your application on a Xeon Phi processor, it's bandwidth bound. You're getting something like 40, 60 out of box, and then 200 if you use the cache mode. That's enough to impress many people, but we are not any people, so we will try to see what we can do to optimize it. First of all, we forgot to go to the high bandwidth memory when we did this run, right? This is in flat topology, and this is all in DDR4 memory. How do we make sure that if we have flat memory topology, we do go to high bandwidth memory? I will do that. So I will request a node in flat mode, but instead of just running stream, I will do numactl -- membind equals 1 stream. So now I'm back to flat memory topology, but instead of running in the on-platform memory, I'm sending code to the high bandwidth memory. And this works out of the box better than the cache mode. So cache mode is convenient, but if you apply a little bit of effort, you can get better results. This is not bad, but I know that I can get something close to 450, 500 gigabytes per second. So there is room for tuning. So what are we missing? We are running the code in the high bandwidth memory. This is how we compiled it. We're using OpenMP. I forgot one important thing. We are running on a Knights Landing processor. So we better tell the compiler to target it. And we can do it using the compiler argument x avx 512. So before that, we were running generic stream benchmark that was the correct syntax is Mike AVX512. No. Sorry, towards the end of the day. This is it. Towards the end of the session, mistakes are more common. So before that, we were running standard code compiled for a general purpose processor. We were tweaking the execution environment by binding it to NUMA node 1, and we were achieving upwards of 300 gigabytes per second. So Nice Landing will support legacy codes to some degree, but we can do better. Okay, we compiled, now we have to resubmit. I'll just type again. Echo. So we're doing NUMA CTL membind 1. 1 is NUMA node 1 high bandwidth memory. Stream QSub nodes, one node with a Nice Landing processor and flat memory. So we're looking to beat these numbers. It looks like we are getting there. Now we're close to 400 gigabytes per second. So two steps that I've made. One is I used NUMA CTL when I run the code. And the second step is I compiled with Mike AVX512. Now the stream benchmark now is running very fast. So it actually doesn't have enough data to achieve the full bandwidth. And this is a recipe that would be difficult to guess, but it's important to know it because when you're optimizing your own code, this is a variable that you can check when you're optimizing bandwidth. The stream benchmark allows me to specify the array size that I want in the command line, in the compilation line, by specifying this preprocessor macro, stream array size. From experiments, I know that 64 million works well. This is a value recommended by Intel. And now I will rerun it. This time it will take a little bit longer, but this is a big enough problem to exploit the size of the system. So we're looking to beat these numbers, and let's focus on the triad test because there's many numbers to keep track of. The triad test is 375. Now it went down. Let me try something else then. I know that what I did is right, but let me try these steps in a different order. How about I just compile like this? But when I run, because this is a bandwidth-bound application, maybe I should set KMP affinity to KMP affinity is set to scatter. How about one thread per core? Hardware subset, one thread per core. This is even worse. A little difficult to demonstrate it. the issue is that when I do both, this is when I get performance benefits. So the stream array size 64, 1, 2, 3, 1, 2, 3. When I do both KMP hardware subset 1 thread per core and stream array size 64 elements, this is where I get to the peak bandwidth. No? I'm missing something else, I guess. Well, anyway, this is a better number than we ever had. The best we had was 375. And now we are at almost 400 gigabytes per second. I'm trying to recall if there's anything I may have left out. And no, I can't recall. So I think that's that's just the model of the processor. If you want to see this demo done right, I have done it right and recorded it, and we have a 2-hour course on Night-Slanting programming here. Colfax Research.com. How can now? The stream benchmark is definitely recorded there. But what I wanted to demonstrate, I did demonstrate. You have to compile so that you target Night-Slanting, and you have to run putting your application in the high bandwidth memory. The trick with putting your application in the high bandwidth memory will only work if you need less than 16 gigabytes of RAM. If you need more than 16 gigabytes of RAM, this is out of the question, and you need to modify your code so that it allocates data in the main memory, but some special data structures go to high bandwidth memory. And I can quickly demonstrate how to do that. This is done with the memkind library, and I will specifically use a simplified interface to the library called hbwmalloc. When I use this interface, I will have to change how data is allocated. Instead of, well, this is before main, so this is just I guess on the stack. I will have to change them to stream type A, stream type B and C. And then I will have to allocate them with a special allocator, but I will have to wait for main to start. Yeah, let's do it here. A, what is the size? A. HBW malloc. HBW stands for high bandwidth. Size of stream type multiplied by stream array size plus offset. This is the special allocator that will put this particular buffer in high bandwidth memory. And I need to repeat this for B and C. If I want to be nice, I need to also deallocate them, but to save time, I will ignore that. So that should achieve the same effect. Only now, when I run the code, well, I have to compile with lmemkind to link the memkind library. Only now, when I run the code, I don't need NumaCTL. So none of this is needed. I just run it normally. Most of the, well, default allocations will go to NUMA node 0, which is the on-platform memory, but these special arrays A, B, and C will be placed in the high bandwidth memory. And I can convince myself of that by looking at the performance values. I'm expecting something of order 400 megabytes per second. Performance drops to 300 gigabytes per second. And this is unfortunate. Why did we lose 25% of performance? This wasn't easy to figure out, but I did with the help of John McAlpin, who is the developer of the Stream Benchmark. The trick here was streaming stores. Streaming stores were actually originally in the code because the compiler was able to clearly see that A, B, and C are all independent from each other, so it is safe to do streaming stores. In our case, when we moved them to the heap, this is no longer guaranteed. So we need to give the compiler additional hints before it can use streaming stores. And there's many ways to do this. One of the hints is a directive, ignore vector dependence. I think it will do the trick. This is the triad test. I think if I put pragma ignore vector dependence, then streaming stores will come back. No, this is add. Triad is this one. So let's see, we are looking at this number and we want it to be closer to 400. Now it's 300 gigabytes per second. No, that didn't work. Something happened, but okay, then I'll go to the route that I know. Okay. The route that I know works is this. When I declare these variables, I will add the keyword restrict. The restrict qualifier promises to the compiler that no other pointer is pointing to the same memory location as this one. It will not compile out of the box because the restrict qualifier is not a part of the C90 standard that the Intel compiler uses by default. So I need to add the keyword, the argument restrict, when I compile the code. Now it compiles, submit for execution, and hopefully this time it will work. Yes, now it worked, and for some reason that I don't understand, it works better than with NumaCTL. But this is a reasonable result that I expect from high bandwidth memory from the triad test. The steps that we did are many, and you can retrace my steps using the recording. So what we did is NumaCTL, then we set the argument xmic avx512, then we set the stream array size to 64 million, then we set KMP hardware subset to 1 thread per core, which we know is good for computationally intensive applications. Then we also went into the code and used HBW malloc. And finally, we had to use the restrict qualifier together with the argument -restrict. I hope I didn't miss anything, did I? I think that's it. And that led us from 40 gigabytes per second to 427. If you have a bandwidth-bound calculation that doesn't perform, see if these aspects are taken into account. You can also experiment with a stream benchmark to see if you can make it like your application, because it allows for tuned tests, which can be anything you want. Today was possibly the most complicated topic of the entire course. We talked about memory optimization. For most of the session, we talked about data reuse and caches. When you have data reuse in the algorithm, you have to rely on caches. There's loop transformations to increase your arithmetic intensity, and there's cache oblivious recursion. In the last half hour, we talked about accessing the main memory. This is what you need to do either if you don't have data reuse in your algorithm, or if it's not possible to easily do tiling. When you access the main memory, to optimize bandwidth, you need to use Unistride, and on top of that, optimize bandwidth, optimize thread count and affinity. Do first touch allocation in NUMA systems. I talked about it earlier in session 9. And when you go to high bandwidth memory, use NumaCTL or memkind. Remember the secret sauce compiler arguments. Some of them are just tuning the instruction dataset, and there used to be some arguments for prefetching for tweaks on Knight's Corner, but I think the compiler takes care of that automatically. And this is actually a true story. We developed these exercises back in 2013, and since then, and back then we had step 1, 2, 3, 4. Since then, the compilers have become much smarter, and we find that steps 1 and 2 are no longer needed because you start at step 3 and the compiler does everything for you. So hopefully what I showed you in this course will be useful at this point. Maybe compilers will be able to do some of this automatically, but it still makes sense to understand what kind of code to feed to the compiler so that it can do the optimizations that you have in your mind. This is the end of the How series. We had 3 modules: how to program something, how to express parallelism, and how to optimize. All the sessions are recorded, and you can come back and revisit them anytime. Thank you for joining us for the How series. This is our trademark training. And we have a series of other presentations that you can watch in recordings or sign up for webinars. I want to tell you about the MC² series, where we invite experts in computational disciplines to talk about code optimization. And what you need to know is that the experts that we've invited the most are people who used to be our students. So people like you who attended the How series, learned something, and then took the knowledge that they had to their domain. They are coming back to report what they did. So you're welcome to join. And we have an open call for proposal for the MC² series. So if you take this knowledge and apply it to your code and have a good optimization story, write to us. We will set you up with cluster access where you can experiment on a variety of architectures. We will help you to prepare the presentation, and you will communicate your work to hundreds and thousands of like-minded professionals around the world, because we do have worldwide audience.